Most people think an air conditioner generates a chilly breeze and blows it into your house, but that's backward. Air conditioning systems actually grab the heat that's already inside your room and drag it outdoors. To picture this, imagine the heat inside a stuffy room as a pile of glowing red boxes. When you turn on your thermostat, you hire a heat mover, a machine whose sole job is to grab those red boxes and toss them outside your walls. The core challenge of climate control isn't creating cold air. The real work is managing the physical logistics and the financial cost of hauling all that heat outside. So if you hire a machine to move heat out of your house, how do you know if it's doing a good job or if it's overcharging you? Engineers use a universal rating system called the Coefficient of Performance, or COP. You can think of COP as the efficiency scoreboard for any cooling system. To get the score, we take the number of heat boxes the machine successfully moves out and divide it by the energy wages we paid it to do the work. If it moves a large stack of boxes for a tiny energy paycheck, the COP number goes up. This score functions as a practical business metric, showing the exact return you get on every watt you buy. In the vast majority of our homes, window units, and refrigerators, we use a standard heat mover called a vapor compression system. These systems rely on a heavy-duty mechanical compressor to do the lifting. They use mechanical force to shove the heat out of your house, which means their wages must be paid in expensive electricity. If you have a compressor with a COP score of 3 and you pay it 10 kilowatts of electricity, it will successfully haul 30 kilowatts of heat boxes outside. These systems are effective at cooling a space, but their physical limits are tied to the utility bill. You have to buy premium electrical power to keep that compressor running. Large industrial facilities have a different strategy. They use a machine called a vapor absorption system, which doesn't rely on an electrical compressor at all. Instead of mechanical force, this system uses a chemical sponge made of a salt called lithium bromide. This chemical naturally wants to soak up the glowing red heat boxes right out of the air. It swells up as it absorbs the heat, without needing a single motor to do the heavy lifting. Eventually, that sponge gets full. To wring it out and reuse it, the system pays its wages using waste heat. By running boiling exhaust gas from a factory generator over the sponge, the system forces the heat boxes outside, shrinking the chemical back to its normal size. A vapor absorption machine usually has a much lower COP score than a standard compressor. But because you are paying the machine with heat that the factory was going to throw away anyway, it ends up being a brilliant financial decision. We can take this moving company logic and apply it straight to a high-level exam designed for professional energy auditors. This is an actual problem from a national certification exam. It asks for the cooling effect of a compression system based on its power draw and motor efficiency. Right at the start of the text, we see a COP of 3.5. Scanning a complex problem for a familiar score like this makes the technical jargon much easier to manage. We already know how this machine operates. First, we calculate the wages paid to our mover. The motor draws 10.7 kilowatts of electricity, but the problem states it runs at 80% efficiency. That means 20% of the power is lost, leaving 8.56 kilowatts of useful energy delivered to the machine. Now we apply our scoreboard. We take our wages of 8.56 kilowatts and multiply them by our COP rating of 3.5. The result is 29.96 kilowatts of heat boxes moved. If we round that up, we can see right here on the test that 30 kilowatts is option A, the correct choice. These problems are often feared, but they are just another way to track the energy you invest against the heat you successfully move.